In this video, I'll show you how to use AWS X-Ray to analyze the performance of a distributed application. This diagram shows the architecture for a version of the Cafe website. This version of the website is more fully developed than the one you have built in the course labs up to this point. In this version of the application, AWS Lambda functions have been built to be invoked when users request information on the Cafe website. These Lambda functions invoke the REST API endpoints that you created in the Lambda lab earlier in this course. For example, when a user loads the Cafe homepage, the getProducts Lambda function is invoked. It performs a lookup in Amazon DynamoDB to retrieve the menu items. Also, as you will see in this demonstration, after authenticating to the Cafe website, an employee can request an inventory report. The request invokes the createReport API endpoint, which in turn invokes a state machine that is defined in the AWS Step Functions service. The state machine runs a workflow that consists of a series of Lambda functions. The functions query an Amazon Relational Database Service, or Amazon RDS, database for the latest report data, and then compile and deliver the report. In this demonstration, I'll configure X-Ray to provide a view of the getProducts API endpoint call results and an end-to-end view of the createReport API endpoint requests. With these views, I'll be able to see the performance and latency statistics of the different services and components involved in these parts of the Cafe's distributed application. Okay, let's get started. So here I am logged in to the AWS Management Console. First, I'll go to the X-Ray console. Notice the links on the left, including service map and traces. As I choose these areas, you see that no data is collected yet. That's expected though, because I haven't instrumented my distributed application yet. Next, I'll go to the Lambda console. Here you see that many Lambda functions are defined. The getRealData function pulls the coffee suppliers data from the Amazon RDS Aurora Serverless suppliers database. The function then invokes the generate pre-signed URL function and the generate HTML function. All three functions are invoked when a report is requested. Separately, the getAllProducts Lambda function retrieves Cafe menu data and displays it on the Cafe website homepage. First, I'll enable active tracing on the getAllProducts function. I choose the function, choose configuration, and then monitoring and operations tools. I'll edit these settings. Then, under AWS X-Ray, I'll set active tracing to on and save the change. Next, I'll follow the same process to enable active tracing on the other three Lambda functions. I'll enable it on the getRealData function, and I'll enable it on the generate pre-signed URL function. And finally, I'll enable it on the generate HTML function. Great. So now I have 4 Lambda functions that X-Ray will collect tracing data for. Now let's go to the Amazon API Gateway console and enable X-Ray tracing here as well. I'll choose Products API and choose Stages, then Prod, and then the Logs Tracing tab. Here I'll choose Enable X-Ray Tracing and save the change. Finally, I'll go back over to the Resources view and deploy the API change to the prod deployment stage. Now, I'll head over to the Step Functions console to enable X-Ray tracing there as well. Recall that the createReport API endpoint will invoke the state machine defined in Step Functions. The state machine will then call the Lambda functions, so it will be helpful to enable X-Ray tracing here as well. I locate the state machine and choose Edit. Then I scroll down to Tracing and choose Enable X-Ray Tracing. Notice the message that displays. To do tracing, X-Ray must have permissions. That's true of all the AWS Identity and Access Management, or IAM, roles that control the permissions of these services that I'm enabling for tracing. They all must have permissions to connect to the X-Ray service. Let's save this change and I'll show you an example of those IAM permissions. Let's return to the Lambda console. Here, I'll choose the getRealData function, configuration, and then permissions. Notice that this function uses a role named role for all lambdas. I'll select that and it takes me to the IAM console. And here in the permissions tab for this role, I'll expand the policy and look at the JSON. Notice that this policy grants X-Ray permissions to the role. That will allow the role to write trace data to the X-Ray service. In a true production environment, I would want to lock down these permissions more tightly, but in this test environment, this will suffice. All the roles that apply to the Lambda functions, Step Functions state machine, and REST API that I've instrumented also have a sufficient level of X-Ray access granted to them for this demonstration. Okay, so now that I've instrumented the Lambda functions, REST API, and the state machine, I'm ready to run some tests. I'll use the AWS Cloud9 IDE to do that because it has a convenient bash terminal that already has account credentials configured in it. However, before I run the test, I need to gather some information from the API Gateway console. I'll choose the Products API, and now I'll choose Get under Products. I need to capture the REST API ID and the resource ID, which are both shown here in the URL. In the text editor, I've already written the command that I will run in the terminal, but I wanted to show you where I got the ID numbers that you will see in the command. Okay, so I'll return to the AWS Cloud9 console and open the IDE where I can run some tests. This code I just pasted in uses the AWS command line interface, or AWS CLI, to test invoking the Get Products API endpoint. Notice the REST API ID and resource ID values. They match the ones I just showed you in the API Gateway console. This AWS CLI call is wrapped in a simple loop that will run the command 10 times. Okay, let's run it. You can see that the CLI shows every time the command invokes the API endpoint. Great. Now let's go check the X-ray console to see if any data is there yet. So here is the X-ray console showing the service map view. Notice that I can set a time range on the view. This is set to show the last 5 minutes. And look at that. The service map shows that the API endpoint I invoked in turn invoked the getAllProducts Lambda function. Lambda shows up here as 2 nodes. The first one, called by the client, is the Lambda service. The second node shows the actual Lambda function I called. The service map shows the amount of time spent on each node. The Lambda service took 322 milliseconds to complete, but the function spent 260 milliseconds of that time. Well, I only invoked the API endpoint a few times. Let's give it a better stress test. To do that, I'll return to the API Gateway console and copy the invoke URL of the getProducts endpoint. Next, I'll return to my bash terminal and use a command called siege. With this command, I can invoke the endpoint more quickly than my earlier loop call to the AWS CLI. This command will simulate 15 users simultaneously hitting the URL repeatedly for 15 seconds. Let's run it. It shows a lot of 200 HTTP response codes. That's a good sign. Okay, now I'll return to the X-ray console and let's see what the service map looks like now. This time the test shows up as a different client. That's because I'm hitting the deployed API endpoint, not using a test invoke method call to the AWS CLI like I did in the prior test. This view shows that the API Gateway service is sending trace data to X-ray. Notice also that the Lambda service is taking a bit longer to reply with this volume of traffic. That's still pretty fast though. Okay, let's increase the load even more. I'll return to the AWS Cloud9 IDE and try simulating 50 simultaneous users. And now let's view the service map in the X-ray console once again. Remember, this Lambda function calls a DynamoDB database table. The numbers change slightly, but they stay in that high 200 milliseconds range for Lambda to respond. The circles remain green, which means that the responsiveness is within the specified parameters. Oh wait, I've refreshed the data again, and now just a bit of yellow is showing up. I'll choose the Lambda function to see details on that. Notice the response distribution view. It looks like the majority of responses were in that millisecond range. However, at least one response took about 3 seconds. Let's zoom in on that. I'll choose View Traces. Because I was zoomed in on these 3-second range responses, those are the only ones that show up in this view of the trace list. There were 5 of them. They all still returned a 200 HTTP response code, so they did respond, but they were just slower. Let's look at the details on one of them. And here is a map of this single trace with a timeline view. If I choose one of the status icons below, it shows subsegment information. Again though, there weren't any errors here, just a bit more latency in the response. Okay, let's go back to the bash terminal and test invoking a more complicated part of the cafe's distributed application, the create report logic. Recall that the create report API endpoint invokes a step function state machine. Here I've got an AWS CLI command that calls that state machine and passes in some test data in JSON format. The command identifies which state machine to invoke by specifying the Amazon resource number, or ARN. It is again in a loop, so that the state machine will be invoked 10 times to simulate some load. That will give us some more data for X-ray to trace. Okay, let's run it. You can see that the CLI shows every time that the state machine that invokes the API endpoint has been invoked. Great, let's return to the X-ray console and analyze the performance of this part of the application. Let's look at the X-ray service map to see what occurred. Notice how this view is collecting, aggregating, and collating information from this distributed application in real time. As you can see, the state machine invokes 3 different Lambda functions and also sends an Amazon Simple Notification Service or Amazon SNS message with a link to the report. The state machine took the longest of all to complete, which makes sense because it doesn't finish running until all the parts of the workflow have completed. The Amazon SNS call was the fastest to run. It took on average only 48 milliseconds. The generate pre-signed URL Lambda function ran very quickly, as did the other functions. Let's return to the terminal and test a bigger load. This time I'll invoke the state machine 20 times. Now back in the X-ray console, I'll refresh again. It looks like the time averages to run each component are actually decreasing. That's great. I've been running tests for a while now. Some of the tests took a bit longer, so I paused the recording for a bit so that they could finish. But let's expand this result set here to include those tests. I'll change the time frame for the service to last 30 minutes. Now look at that. The other 2 Lambda functions still consistently completed quickly, but the average time over the last 30 minutes for the getRealData Lambda increased quite a bit. It took on average 1.19 seconds to complete. Let's choose the node the furthest to the right on the map. It took the longest. It's the getRealData Lambda function. Because it takes longer to complete, it causes the upstream nodes to complete more slowly. So X-ray helps me pinpoint a performance bottleneck relative to the rest of the application. Remember, this is the Lambda function that performs the database lookup in Amazon RDS to get the data that will be sent in the report. And here I can see that 89% of the time, this function performed well. However, it has an 11% error rate. I'll select the box next to the error response and then view those traces. Here I can see that 5 traces are in the dataset. If I group them by response time root cause, they are all part of the same group. I'll dig into the details on one of the traces in the trace list. Next, I'll choose the status icon in the Lambda function row that shows the red exclamation point icon. In this subsegment details view, on the exception tab, a message and cause show. It looks like a timeout error occurred, perhaps related to the database connection. This could be due to a number of reasons, and I could set up more specific tracing to get to the root cause of the timeouts. Perhaps it's due to a networking configuration issue between where my Lambda function is running and where the Amazon RDS database is running. Or maybe I should check my Lambda function code and confirm that the function that opens the database connection is coded outside of the function handler so that it doesn't close the connection every time it is invoked. There could be other reasons. Obviously, I would need to spend some time to look into this further. I could run more tests and sample a larger time frame. I could try to determine if there's a correlation between how many requests I run in a short period and how frequently this timeout error occurs. I could also use the X-ray SDKs to instrument my code within the Lambda function. This would provide even more trace data to help locate the root cause. I'll show you some code snippets in a moment that would get you started with that. But let's just take a moment here to recognize that by just checking a few boxes in a few AWS service consoles with no changes to any of my code, I was able to instrument many parts of my distributed application with X-ray. And X-ray has quickly given me insight into which parts of the application are prone to experience excessive latency or produce errors. For example, before instrumenting the application, I did not know which of the 3 Lambda functions was taking the longest to run. If a report did not arrive, I didn't know where to start looking. Now I do. I'd like to show you one last thing. Notice in the X-ray console, if I choose Getting Started, it prompts me to either launch a sample application or instrument my own application. If I choose the Instrument My Own App, it then prompts me to choose a language. I'll choose Python, and here you see that if I have an already built application in Python, I could instrument the incoming HTTP requests by using the provided Django middleware code. This screen also provides the commands I could use to download the AWS X-ray SDK libraries. If I import the SDK into my code, I could then update my application to use the classes and methods that the SDK provides to generate and send trace data to the X-ray daemon. Finally, there's code that shows how to run the X-ray daemon on an Amazon Elastic Compute Cloud or Amazon EC2 instance, in an Elastic Container Service or Amazon ECS container, or as part of an AWS Elastic Beanstalk application. The options for Lambda reference the documentation, which describes how to enable X-ray tracing on Lambda functions, just like I did in this demo. As you can see from the options on this screen, if you want to, you can configure tracing of events not only at the AWS service level, as I did in this demo, but you can further define custom traces in your application code. In summary, you've seen how to instrument a distributed application to share trace data with X-Ray from Lambda, API Gateway, and step functions. You've also seen how X-Ray is able to create a service map of the application to deliver insights into the performance of the different parts of the application over different time frames. You've also seen how you can drill down into trace data to gain insights about your application's performance. That concludes this demonstration. Thanks for watching.
Let's review the module and wrap up with a discussion of a practice certification exam question. In this module, you learned how to explain serverless computing, describe how Lambda works, recognize Lambda invocation models, identify how to use IAM to grant Lambda permissions, indicate the steps to author and configure a Lambda function, explain how to deploy Lambda functions, identify why X-Ray is a critical developer tool, and create Lambda functions. Now, let's take a look at a sample exam question. A developer is testing an application locally and has deployed it to Lambda. To remain under the package size limit, they did not include the dependencies in the deployment file. When testing the application remotely, the function does not run because of missing dependencies. Which approach would best resolve the issue? A. Use the Lambda console editor to update the code and include the missing dependencies. B. Create an additional .zip file with the missing dependencies and include the file in the original Lambda deployment package. C. Add references to the missing dependencies in the Lambda function's environment variables. Or D. Create a layer that contains the missing dependencies and attach it to the Lambda function. Note the key requirements stated in the problem. The solution needs to stay under the package size limit and needs to include the dependencies. Consider the answer choices and rule them out based on these requirements. Let's pause for a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. So how do these answer choices compare to the requirements? Option A, use the Lambda console editor to update the code and include the missing dependencies. This would not meet the requirements because if the dependencies are added in the Lambda console editor, then they will become part of the deployment file and the package size limit will be exceeded. Option B, create an additional .zip file with the missing dependencies and include the file in the original Lambda deployment package. This would not meet the requirements because this approach would also add to the size of the deployment package. Option C, add references to the missing dependency in the Lambda function's environment variables. This would not meet the requirements because an environment variable is simply a pair of strings that is stored in a function's configuration. The max size of all environment variables associated with a function is 4 kilobytes. The correct answer is D. Users can configure an AWS Lambda function to pull in additional code and content in the form of layers. A layer is a .zip archive that contains libraries, a custom runtime, or other dependencies. With layers, users can use libraries in a function without needing to include the libraries in a deployment package. Thank you for completing Module 7, Developing Event-Driven Serverless Solutions.
In the physical world, a container is a standardized unit of storage. Container sounds like a generic term, but its importance is more clear if you look at how containers changed the shipping industry. Before the introduction of the modern shipping container in 1956, transporting goods from one point to another was a challenge. Goods were shipped in sacks, crates, cartons, drums, casks, barrels, and boxes of various weights, shapes, and sizes. They often were loaded by hand into whatever vessel was carrying them. The vessel wouldn't know how much cargo it could take until all of the cargo was loaded. Transporting goods this way was slow, inefficient, and costly. Shipping containers revolutionized the shipping industry. Their uniform size made it much more efficient to load, unload, and stack them. Containers could also be easily moved between ships, trucks, and railroad cars. In this way, containers improved efficiency, increased productivity, and reduced costs. This is a great example of using abstraction to increase agility. Abstraction is a way of hiding the working details of a subsystem. It separates concerns to facilitate interoperability and platform independence. In the shipping example, abstraction means that the people involved in shipping are further removed from the details of the transaction. This abstraction applies to the people who send the contents and those who actually facilitate the shipping itself. They don't need to worry about whether items will fit in a given container or about the fit of the container onto various vessels. This concept can move from the physical world to the virtual world of computing platforms. Virtually, a container is a standardized unit of software designed to run quickly and reliably on any computing environment that runs the containerization platform. Containers provide operating system virtualization, or OS virtualization, so that you can run an application and its dependencies in resource-isolated processes. A container is a lightweight, standalone software package that contains everything a software application needs to run. For example, it can contain the application code, runtime engine, system tools, system libraries, and settings. Containers can help ensure applications deploy quickly, reliably, and consistently, regardless of the deployment environment. A single server can host several containers that all share the underlying host system's operating system kernel. These containers might be services that are part of a larger enterprise application, or they might be separate applications that run in their isolated environment. Increasing levels of abstraction are often associated with technical maturity. The move toward containers is part of the evolution of deployment models. In earlier phases, you had bare metal servers. You had to build the architectural layers, such as the infrastructure and application software layers. For example, you would install an OS on top of your server hardware. Then, you would install any shared libraries on the OS and then install the applications that use those libraries. This architecture was inefficient. In this model, your hardware costs are the same, whether you are running at 0% utilization or 100% utilization. All of your applications must compete for the same resources, and you must keep library versions in sync with all your applications. If one application requires an updated library version that's incompatible with other applications running on that host, then you run into problems. These shortcomings led to the use of a virtualization platform over the host OS. Now you have isolated applications and their libraries which have their own full OS inside a VM. This arrangement improves utilization because you can add more VMs to run on top of the existing hardware, which greatly reduces your physical footprint. The downside to VMs is that the virtualization layer is heavy. In this example, you now have 3 operating systems on the physical host server instead of 1. That means more patching, more updates, and significantly more space taken up on the physical host. It can also cause significant redundancy. You've installed potentially the same OS 3 times and potentially the same library 3 times. Containers improved upon the idea of virtualization. The container runtime shares the host operating system's kernel. You can use this arrangement to your advantage to create container images by using file system layers. Containers are lightweight, efficient, and fast. They can be started up and shut down faster than VMs, which means better utilization of the underlying hardware. You can share libraries when needed, but you can also have library isolation for your applications. Containers are also highly portable. Because containers isolate software from other layers, their code runs identically across different environments, from developing and staging all the way to production. Here are the key takeaways for this section of the module. A container is a standardized unit of software that contains everything that an application needs to run. And containers help to ensure that applications deploy quickly, reliably, and consistently, regardless of the deployment environment. Thanks for watching, and see you in the next video. Section 4, Using Containers for Microservices. One of the strongest factors driving the growth of containers is the rise of microservice architectures. Microservices are an architectural and organizational approach to software development, designed to speed up deployment cycles. The microservices approach fosters innovation and ownership and improves the maintainability and scalability of software applications. Consider this example of a traditional monolithic architecture. For this shopping application, all of the processes are tightly coupled. With tightly coupled processes, if one application process experiences a spike in demand, the entire architecture must be scaled. Adding or improving features becomes more complex as the code base grows, which limits experimentation and complicates the implementation of new ideas or technology stacks. Monolithic architectures also add risk for application availability because having many dependent and tightly coupled processes increases the impact of a single process failure. Now, consider having the same applications run in a microservice architecture. Each service is built as an independent component, which communicates by using lightweight API operations. Each service performs a single function, which could support multiple applications. Because the services run independently, they can be updated, deployed, and scaled to meet the demand for specific application functions. When you consider the characteristics of a well-designed microservice architecture, containers are well matched to support microservices. Microservices are decentralized with an evolutionary design. This means each container can use the language and technology best suited for the service. Microservices provide smart endpoints and dumb pipes. Therefore, each component or system in the architecture can be isolated and can evolve separately. Microservices are independent products, not projects, so you can package all your dependencies and libraries into a single immutable object. Microservices are also designed for failure. You can shut down a container when something goes wrong and create a new instance. You start fast, fail fast, and release any file handlers. Microservices are disposable. The development pattern is like a circuit breaker. Containers are added and removed. Workloads change, and resources are temporary because they constantly change. Finally, microservices offer development and production parity. Containers can make development, testing, and production environments consistent. This consistency facilitates DevOps, in which a containerized application that works on a developer system will work the same way in production. Thanks for watching, and see you in the next video.